Okay, so again it is from gas power cycle. In the previous class we already discussed about the diesel cycle and how to analyze the diesel cycle efficiency and different parameters. Okay, and also we look for the TS and PV diagram in the previous lecture number 11. Okay, so this lecture is also related to your diesel cycle. So we will see that some different sort of problems of diesel cycle. So in this class we will also solve some sort of problems. So first you have to read the statement. Okay, so this question is also related to diesel cycle. An air standard diesel cycle has a compression ratio of 18.2. Air is at 20 degrees Celsius and 60 kilopascal at the beginning of compression process and at 1300 degrees Celsius. So it's mean that your temperature at point number one and pressure at point number one is given in the question, and also at 1300 degrees C at the end of heat addition process. Mean that your T3 is also given in the question. So accounting for the constant specific heat with temperature, so determine the cutoff ratio. So here the difference between the previous question is that here we have to find the RC, which is the cutoff ratio, which is the ratio between your cutoff point, volume at the cutoff point V3 to minimum volume, which is the volume at TDC, V2. The heat rejection per unit mass and thermal efficiency. Okay, so this is your problem statement, and now we will try to solve the problem. Okay, so starting from the PV diagram, and an important thing is that I have noticed that when I assigned the question in the previous class, most of the students draw the PV diagram wrong. Okay, so keep it practice that you have to draw it right. Otherwise, it's mean that you have no understanding of the cycle. Okay, so if there will be constant pressure process, you have to draw constant pressure like a straight line. Do not draw some random line that it will be representing the constant pressure. So it will be the wrong process. Okay, and in the your sessional exam or any final exam, it will be a negative marking on if you have made the wrong PV diagram or TS diagram. Okay, so here we have to draw the PV diagram for the diesel cycle first, then we will solve the, so this is your P and this is the volume, and then we already know that first process is the compression process, so you can just draw point like this 1 to 2, which is your isentropic compression process. Then in the diesel cycle, and there will be constant pressure heat addition, so it's mean that 2 to 3 will be here. Okay, so at this point you can say 2 to 3, and then there will be expansion process, isentropic expansion, and the temperature will be and your volume will be same as of V1. Okay, so it's mean that your point, that is number 4, will be in line with this point number 4. Okay, point number 1, sorry. Okay, and you can just draw like this. Okay, so this point number 1 and 4 will be aligned because this is the constant volume heat rejection process, QR, and this is your point number 4, and you can just say this is your expansion process, this is the compression process, and this is your Q in. Okay, so this is how we have to draw the diesel cycle PV diagram. Okay, so starting from that data from your problem statement, so in the question it is given that your point number 1, at the start of your compression process, the temperature is given, so T1 is equal to 20 degrees Celsius, so which you can convert into Kelvin, it will be 293 Kelvin, and then the pressure at number 1 is also given, which is 60 kilopascal, and then temperature at point number 3, which is at end of heat addition process, is also given in the question, which is 1300 degrees Celsius. You can convert it into the Kelvin and you will get 1573, and also the compression ratio is mentioned in your question 18.2. Okay, so it's mean V1 or V2 is given in the question. So part A is to find the cutoff ratio. Okay, so in order to find the cutoff ratio, we already know that the cutoff ratio is the ratio of cutoff point volume at cutoff point to your minimum volume, which is volume at TDC, which is V2. Okay, so we have to find this ratio. So in order to find this ratio, again we have to apply first the isentropic process, the relationship for the isentropic process, V1 or V2. Okay, and specific heat ratio K minus 1. Okay, so V1 or V2 is given in the question, which is 18.2, and you can say that T2 is equal to T1 293 Kelvin, and then 18.2, 1.4 is the K value minus 1, and you can just solve it and you will get 939.2 Kelvin. Okay, so now we have to apply because we have to find the V3 or V2. So it means that we have to apply one relation between point number 3 and 2. Okay, so for the gases, we already know that the relation that is valid is P3 V3 over T3 is equal to P2 V2 over T2. And from this, you can already know that P2 is equal to P3. So it's mean that this term is automatically eliminated over there. If it is eliminated, it's turned out to be that you can say that V3 or V2, which is your RC cutoff ratio, which we have to find, T3 over T2. Okay, so you can just divide these two temperature and you will get the value of your cutoff ratio. Okay, so you can note it down, then we'll move towards the next part. And if you can just divide it, you will see that T3 is given in the question. It is mentioned that at the end of your heat addition process, the temperature is 1300 degrees Celsius or 1573 Kelvin. So you can say 1573 over T2 value we already find out here. So you can say 939.2 Kelvin, and you can just divide it and you will get the RC value as 1.674. Okay, so this is your RC value and the part A solution is done. So now we will move towards the part B. So you can note it down, then I will move towards the next one. So here the PV diagram is clearly drawn over there, so you can just correlate with it. Okay, so B part, we have to find the Q out. Okay, so in order to find the Q out, we already know that Q out is equal to this constant volume heat rejection process and T4 minus T1. Okay, so this relation we already know, and here we already know the T1 value from the problem statement. T4 value we have to find, and for T4 value you can apply the isentropic relation between 4 and 3, and T4 over T3, V3 over V4, K minus 1. Okay, and you already know that RC is equal to V3 over V2, and you can say V3 is equal to RC into V2. Okay, so RC value already known to us, so you can put the V3 value in the equation. You can say equation number 1, and you can find as T4 is equal to T3 1.674 V2 over V4, and you can say 0.4 1.4 minus 1. Okay, so now from there you can notice that V4 is equal to V1, and if we just take this part in the denominator, so it becomes the compression ratio. Okay, so T3 value is known to us already, so 1573 1.674, and it will be divided by the compression ratio 18.2, and 0.4 is the 1 minus 4 minus 1. So if you can solve it, you will get 605.6 degrees Celsius. So it's mean T4 is known to us. So from here we can easily find Q out. CV value is 0.718, 605.6. Okay, sorry, this is a Kelvin. And this is 293. Okay, and from here you can just solve it and you will get Q out value 4.46 kilojoule per kg. So which is mentioned in your question. So you have to find the Q out in per unit mass. Okay, so if it is mentioned per unit mass, you can just kilojoule per kg. If it is in the kilojoule, you have to multiply the mass fraction as well. So you can note it down, then I will move towards part C. so part number C is the efficiency. In order to find the efficiency, 1 minus Q out over Q in. 1 minus 636.9. 1 minus 0.35, and which is 65%. Okay, so this is the solution. And also you can use the relation which we already developed, which is in the function of R and RC. Okay, so which we already developed in the previous lecture, because it is a constant specific heat ratio problem. So you can, this relation is valid for that sort of problem as well. If you have any question, you can also ask me. Okay, so moving towards another question. So it is again related to the diesel cycle. Okay, so first you have to read the statement, then I will move towards the solution. So a 4-cylinder 2-stroke 2.4 liter diesel engine. Okay, so in this question, whenever it is mentioned that the volume of your diesel engine is this, so it's mean that the maximum volume, which is at V1, is 2.4 liter. Okay, diesel engine that operates on an ideal diesel cycle has a compression ratio of 17, so R value is known. Cutoff ratio is also known. Air is at 55 degrees Celsius and 97 kilopascal. So it's mean that your temperature at the beginning of process and pressure at beginning of process, which is point number 1, is given in the question. During the cold air assumption, determine how much power engine will deliver at 1500 rpm. Okay, so this is your question. And before starting this question, you have to know that I already mentioned, I think in lecture number 9, that when there will be 2-stroke engine, the one cycle in the one cycle there will be 1 revolution, okay, of your crankshaft. And when there will be 4-stroke, in one cycle there will be 2 revolution for your crankshaft. Okay, so this data we have to use in this question, because here it is mentioned 2-stroke and we have to find the power of the engine. So we will see how to implement this thing in the problem as well. Okay, so now coming towards the solution. Okay, so again you have to just correlate with the PV diagram of the diesel cycle. Okay, so in order to find the power, so power you can say W dot net, okay, or you can say WRP, okay, is equal to N W net out okay, so you can say R. Okay, so here if you have noticed that there will be N. Okay, so this N come from the RPM, which is mentioned in your question, rotation per minute. Okay, so you have to convert into revolution per second. Then W net out, you already know that W net is equal to Q in minus Q out. And then the term R. Okay, so this term R is defined as the number of revolution in your one cycle. Okay, so which I already defined in the previous slide. So for 2-stroke, it is equal to 1. If it is 4-stroke, it will be 2. Okay, so in this case it will be 1, so your relation will be N into W net out. Okay, so you have to keep it, remember that this will be how much revolution in the 2-stroke and how much revolution in the 4-stroke. Okay, so starting from the solution, so in order to find the Q in and Q out, we have to find out temperatures at all the points. So again, we can apply for the isentropic process T2 over T1, V1 over V2, specific heat ratio -1. Okay, so from the question, you already know the temperature at the start of compression, which is T1. It is mentioned in the question as 328 Kelvin, and also compression ratio is given 17, 0.4. Okay, and you can just solve it and you will get the value of T2 as 1019 Kelvin. Okay, so now again we have to find the T3 as well, because we have to find all the temperature. So in order to find the T3, you can implement the relation between 3 and 2. P3 V3 over T3 is equal to P2 V2 over T2, and this will automatically eliminated, and it turns out to be T3 is equal to V3 over V2 T2. Okay, and from here T3 is equal to, and this is the cutoff ratio which is mentioned in your question as 2.2. So 2.2 into 1019 Kelvin, and that turns out to be 41 Kelvin of your T3. Okay, so this is your T3, so you can note it down, then I'll move towards the next slide. this is coming from process number 3 to 4. Okay, so now we have to find the T4 as well. So T4 is equal to, for isentropic process, V3 over V4, specific heat ratio minus 1, and you can say T4 is equal to T3. Okay, and as we already practiced in the previous question, that V3 is equal to RC value 2.2 into V2 over V4, and you can say it will be 0.4. Okay, and V4 over V2 is the compression ratio, so T4 is equal to 41 2.2 over 17, 0.4, and that turns out to be 989.2 Kelvin. So now this is the part, and then okay, another important thing is here for the W net, which I already mentioned in the W dot net, which is the power equation. So you have to use the W net in the kilojoule. Okay, so in order to find the kilojoule, you have to find the mass as well, mass fraction as well of your working fluid. So P1 V1 over RT1. Okay, so 97 kilopascal is mentioned in your question. It is a P1 at point number 1. Okay, so here V1 is the volume which is at initial state, which is given in your question. It is a 2.4 liter engine. Okay, so you have to convert it into the meter cube. And then R value is the gas constant, 0.287, and T1 is also mentioned in the question, 328 Kelvin. Okay, so you can just solve it and you will get the value 2.473 into 10 raised to the power minus 3 kg. Okay, so now coming towards the Q in. So from here you can easily find Q in as well and Q out also. Okay, so for Q in, it will be M Cp T3 minus T2. So it is a constant pressure process, that's why we have to use Cp value. So M is already known to us, 2.473, 10 raised to the power minus 4. Cp value you can find out in table A2, or you can remember it. And T3 value is 2241 minus 1019 Kelvin. Okay, if you can just solve it, you will get the value of Q in as 3.038 kilojoule. Okay, so this is your Q in value, so you can note it down, then I'll move towards the next. Okay, so now moving towards Q out. So Q out is equal to M Cv T4 minus T1, which is the constant volume process, heat rejection process. So here M is known to you, 473 into 10 raised to the power minus 3. Cv value is 0.718, T4 value is 989.2, and T1 value is 328 Kelvin from your problem statement. So it turns out to be 1.174 kilojoule. Okay, because all the process we have done, because we have to find W net. So W, so you can just say, because if it is a dot, it means it will be in per unit mass. So here it is not in per unit mass, so do not put dot over there. So Q in minus Q out, and you can just subtract two values, 0.3.038 and 1.174. That is 1.864 kilojoule. Okay, so this is your W net, and now you can use the equation which I already described in the first start of the example, which is W dot net, which is the power, which is equal to N. This is your revolution per second, and this is W net, which is your total work. So N is in the question it is mentioned 1500 RPM. So by just dividing with 60, you can easily convert into revolutions per second. Okay, and W net is in kilojoule, 1.864, and now you can just multiply this and you will get 46.6 kilowatt. Okay, so this is your power. that engine will produce during one cycle. Okay, so if you have any question, you can ask me. And another important point over there is, if you can notice that if there will be a four-stroke engine, for example, it is a four-stroke engine, so we have to divide with the two. So it means that the power produced in the four-stroke engine is less as comparison to the two-stroke engine. So that's why this is the advantage of two-stroke engine. That two-stroke engine produce more power as comparison to the four-stroke engine. But at the same time, the wear and tear in the two-stroke engine is more because it produces more power. Okay, and there will be so that's why it is not used in the automobile as well as in the comparison of spark ignition engine, because spark ignition engines are more reliable and durable as comparison to stroke engine two-stroke engine. So this is the question which is related to your two-stroke as well, and also we have calculated the power. So if you have any question, you can also ask me.
सर वो क्वेश्चन जो था सर इसमें सर स्टेटमेंट दिखा रही है।
अच्छा, मैं दिखाता हूँ अभी आपको पता चलेगा इससे। Okay, here statement.
तो सर जो पहला क्वेश्चन किया
जो पहला क्वेश्चन किया था,
जी सर ठीक है सर।
okay, so I hope there will be no question regarding these questions, these problems which we already solved. Okay, so now this is the question which you have to solve. Okay, so it is a similar question which I already solved in the previous slide. So a four-cylinder, two-stroke, 3.2 liter engine, diesel engine that operate on an ideal diesel cycle has a compression ratio of 15. So same thing, only the data is changed. Cutoff ratio is 1.9. Air is at 65 degrees Celsius. 87 kilopascal is your T1 P1. At the beginning of compression process, using code air assumption, determine how much the engine will deliver at 1700 rpm. So you can proceed with this example, and you can send it to me by the tonight or by tomorrow. Okay.